It's nice spring weather. Weekend begins on Thursday evening, so we're in the middle of the weekend. I appreciate your coming. All right. Where things left off last time, I was trying to finish up talking about radio and how radio is used to convey information. Initially sound. In fact, this is the same story for the broadcast of any information by way of electromagnetic waves. And that means that's Wi-Fi, that's all the wireless data transfers around. They all take roughly the same path. So here's the story. At this point, I hope you have a decent understanding of how a radio wave travels, how you launch one, how you receive one. Any questions about those to start with before going? I'll remind you, I will remind you that it helps in transmitting and receiving waves to use resonant antennas where that have a natural motion of their electric charges up and down that are in sync with the wave you're either trying to transmit or trying to receive. And antennas that do that are, if it's a full antenna, that is both sides of the antenna, one side that goes positive, one side that goes negative, and then they reverse. If it's a full antenna, it's half a wavelength long. That is half the wavelength of the wave it's trying to transmit. That's how long the wire is. And if you want to use half that antenna, you can by slicing this half wave antenna in half and putting a conducting surface on the bottom, which acts as a mirror and creates in its reflection the missing half of the antenna. So quarter wave antennas are pretty common. In the era during which radio sort of developed, you had to use tricks like that. You had to use resonant antennas because the electronics wasn't sophisticated enough to dig the tiny radio wave signals out when you didn't have the help of these various of those tricks. Modern electronics is getting so good that some of the equipment that you use just sort of ignores those rules and manages to pull things off anyway. So most of the antennas on cars now are pretty short, stubby things. They're too short to be resonant at the frequencies that they're trying to receive, and they get away with it anyway. They manage to dig these tiny little electromagnetic effects, the motion of not enough charge on their antenna. They're able to see that anyway. So things that I claim you have to do, more and more they get buried. They disappear as technology advances, become invisible. All right. Transmitting information. A radio wave by itself doesn't transmit any information. It's just a steady, unvarying electromagnetic wave. Just this wave from the laser pointer there, although what does that have to do with a radio wave? Well, it's an electromagnetic wave. It happens to be at higher frequency to the point where we can see it as green light, and we'll get to light shortly. But that wave carries no information because it's always the same. And to make it carry information, we want to change it with time, so blink it on and off. Now, I can send Morse code this way. And basically, radio waves do that same trick. And again, radio developed in the days of relatively simple, even primitive electronics. And so they had to work with what was doable at the time. And the two methods for conveying sound information by radio wave that developed in the previous century were AM and FM. That is amplitude modulation and frequency modulation. And I got started on this last time at the very end of the hour, and I'll rehash it anyway because there are things worth saying. Amplitude modulation or AM modulation encodes sound information, and it can encode other things, but sound. Let's start with sound by varying the intensity of the wave. In fact, how bright it is. If you could imagine seeing a radio wave. You vary the strength of its electric field, and corresponding its magnetic field goes with that, to encode pressure variations that are sound. So if a microphone is listening to me, which is actually the case, so a microphone is listening to me talking, and as it's doing that, it's essentially measuring the variations in air pressure around the average, the ambient pressure. Sometimes the pressure is a little high, sometimes it's a little low. It's making those measurements, and initially it represents those variations in pressure as variations in electric current or possibly in voltage. It depends a little bit on the details, but not so important. Eventually, though, if it goes to become a radio, if you want to use a radio wave to encode it, which is actually also the case since it's a wireless microphone, you have to do something to the radio wave to represent the high pressures and low pressures. AM modulation is one reasonable choice. And in that representation, you turn up the intensity to represent pressures, say that they're above average. And you turn down the intensity to represent sound pressure levels that are below the average. You know, whether it's above or below, that's a matter of the details of the processing, the electronics. It's not important. You just vary the intensity of the wave to represent the variations in pressure. Is that okay so far? More questions about that idea? So that's AM modulation. It has, for long-standing historical, conventional reasons, there is a band of the electromagnetic spectrum that's been allocated, certainly in this country and I think in most countries, to transmit sound by way of AM modulation. We talk about it as the AM band. It lives around 1 million cycles per second. It's a little below, a little above. 1 million cycles per second. And by convention, sound goes over those by varying the intensity of the wave. All right? So, some details about that. On the grand scheme of things, it's a pretty narrow range of frequencies. It goes from 550,000 cycles per second to 1.6 million cycles per second. It's not a lot of different frequencies, really, as compared to things like Wi-Fi. Why does that matter? Well, there are a lot of AM stations around sharing this same territory. And by convention, also, each radio station has been allocated only a narrow patch of frequencies around a center frequency. The center frequency is the one that they announce. So I'll pick one that I happen to know in town. WINA is 1.070 million cycles per second. WINA is allocated official frequency. The act of taking their radio wave and winking it on and off a little bit, little bright, little dim, little bright, little dim, that act actually affects the frequency of their transmission. It's not a pure tone. If you think, I like to think of it as tones, like as though you were hearing a flute play. A flute play is a pretty pure sound tone. So a radio station which is representing no sound, just transmitting away, transmitting silence, will be sending out a pretty pure tone. In the case of WINA, it would be 1.070 million cycles per second. But as soon as they start to play with it, they wink it on and off a little bit. It's not a pure tone anymore. That warbling effect necessarily spreads out the frequencies that they're transmitting. They're not transmitting one pure frequency. They're transmitting a range of frequencies. And if they're trying to represent, let's say, a 500 cycle per second musical note, then that action will put on additional frequencies onto the wave they're sending that correspond to 500 cycles per second more and 500 cycles per second less than the note they're normally sending, than the frequency they normally send. They ultimately end up using a band of wavelengths. So the word band starts to show up. You've heard of the notion of bandwidth. People talk about bandwidth as though it's, they use it in casual language. Well, this is really starting to get to be the meaning of bandwidth, that an AM station is allocated, I believe it's 5,000 cycles of bandwidth, so that they have, I think it's 2500 above and 2500 below their official frequency. That's all they're allowed to work with. And that limits them to being able to work with music. If they're trying to represent music, they can't go higher than about 2500 cycles per second in music, which is, it's a high pitch, but it's not, it's present in our voice, particularly in things like S's and some I guess, sibilant sounds. There are high frequencies there. And when you say them and when they are represented then with an AM transmission, they take its central frequency and they put on portions that reach out above in frequency and below in frequency, almost to the edge of what they're allowed to work with. Is that okay, the idea that adding sound and encoding sound by AM modulation technique spreads out the range of frequencies? This is pure mathematics. It shows up if you just try to represent if you take a pure sine wave, which is what we've got up there on the top, a pure sine wave in time, and you try to add on top of that other frequencies, you spread out the frequency. You try to encode frequency. I'm not saying this well at all, but when you've taken this frequency down here and you've winked it on and off, this contains frequencies. This function, as a function of time, contains frequencies that are above and below the frequency that would be present if it were just pure and steady. Anyway, what does this mean in practical terms? It means that AM radio is not even permitted to include frequencies above 2500 cycles per second in sound. And that limits its ability to present music. So AM is not very good for music. It's fine for voice. And that's what it's used for, by and large. Some stations will try to put music on, but it's not going to be very good music. I mean, well, it can be great music, but it won't come across very well. So that's a starting limitation. The other things to put into this story, the AM modulation technique means that a station is there winking on and off their radio wave. There are times when the radio wave is quite weak, right? When they're trying to represent, say, perhaps low pressures. The wave is quite weak, and there's a limit to how weak they can make it before it just stops being there at all. So they have to be careful not to what's called overmodulate, where they go from high intensity to low intensity. They go too far, and they actually shut off their transmitter at times, or go beyond what their transmitter can provide. If they do that, the sound will start to become distorted. So they're monitored to make sure they don't overmodulate, because the act of overmodulating also puts frequencies into their wave that they're forbidden to include. Next thing to talk about is the receiver of the AM radio wave is looking for a wave at the frequency that the transmitter is supposed to be transmitting. So you dial your knob or you tune your buttons to try to look for that wave as opposed to other waves. And there's a filtering process that tries to distinguish the wave that's coming from the station you're trying to listen to from all the other stations. Nobody else is supposed to be in this same territory. But if you're getting pretty far away from the transmitter and there's another transmitter sharing the same frequency out in Kansas or maybe somewhere, Vancouver or something, the little bit of that wave that's still getting to you, and I can talk in a minute about the waves get weaker with distance, the little bit of the wave that's getting to you from this distant station also shows up at your receiver, drives charge up and down your antenna, and there's nothing in this scheme that allows your receiving radio to distinguish the station you want to listen to from the station you don't want to listen to. They're both at the same frequency. They're both pushing charge up and down your antenna. You see, your radio detects them both and adds them on top of each other. You hear both. So with AM, you've probably had this experience, if you still listen to AM radio, where you are listening to one station, but there's sort of background talking or something. Like there's a second station coming in weekly, but it's there as well. And no mechanism to remove it, distinguish one from the other. Is that familiar to some people, the overlap that you get with AM? The other thing is that anything that transmits an electromagnetic wave within that 5,000 cycle per second swath allocated to the station you're listening to, anything that transmits in that range will introduce additional sound into what you're listening to, even if it's just random stuff, like a badly functioning gasoline lawnmower. Lots of things create electromagnetic waves. Anytime electric charge accelerates, it creates electromagnetic waves. So if you've got stuff like the sparks associated with the spark plugs in a lawnmower, that sparking effect, or cars as well, the sparks involve accelerating electric charge. They transmit electromagnetic waves. And it's easy enough for those waves to include frequencies that are in the range that your AM receiver is trying to receive, and you'll hear them as noise. Lightning strikes, same thing. You hear them as noise in your AM receiver. So AM radio, it's essentially forbidden from being good for music because of its limited bandwidth. You've only got 5,000 cycles per second to work with, that range around the center. It has very little ability to filter out random noise from just electric junk around the world and other stations. That's most of the story. I got one last thing to talk about is that you also, sometimes near sunrise or sunset, you can hear stations that are very far away because the waves bounce off of a layer of the Earth's atmosphere known as the ionosphere. They will actually go up there and that will act as a mirror for them. They come back down, having gone up and gone down. You can hear a station that should be way out of view and for you, allowed to sort of go around the surface of the Earth by way of reflection. Hopefully that's familiar as well. Any questions about AM radio then? Before I can finish up with that. Okay. Can you do better than AM radio for transmitting just sound? And the answer is yes. And the first step to do better is to go to what's called FM modulation, frequency modulation. Don't wink the transmitter on and off, and therefore spend part of the time sending a very weak wave. Keep the wave on full blast, but change its frequency very slightly around the official frequency that you're allocated. And the FM technique, by long-standing convention, is used in a band that we often call FM radio that runs from about, is it 88 megahertz? A megahertz is a million cycles per second. So 88 million cycles per second up to 108 million cycles per second. So it's much higher frequencies. And the range of frequencies there from 88 to 108, that's 20 million cycles of difference from one end to the other. That's a pretty big swath of electromagnetic spectrum, 20 million cycles wide. Whereas the AM band, being down at very low frequencies and covering a small territory, it's only about 100, it's about 1 million cycles wide, much narrower. So the FM radio spectrum, it's allocated in much bigger chunks. So when you file and get a license to transmit it in the FM, I think it's 200,000 cycles wide. These numbers I used to remember clearly, and then after a while they get all fuzzy. So you're allocated 200,000 cycles, and that may actually be above and below. But in any case, it's a big chunk of spectrum that you're allowed to work with. And because of that, you can represent music nicely. You can represent high frequencies very effectively. The FM technique takes your center frequency that you've been allocated, and it allows you to vary the frequency of your wave a little above and a little below. And it's either as much as 100,000 cycles above and 100,000 below, or it's 200. I can't remember which. Doesn't matter. So you can go up and above and below, and as you move the transmission frequency around dead center, you're representing, in the case of music, you're representing higher pressures by going, say, to higher frequency, and lower pressures by going to lower frequency. So you're warbling back and forth with the wave you're transmitting in order to represent sound pressure fluctuations above and below average. It's okay? This technique is pretty good at transmitting sound information without much sensitivity to noise. That is, your radio, particularly modern radios, are pretty good at focusing in on the transmitted wave coming from one station and ignoring everything else. How do they do that? They watch the wave as it comes in, and they're looking for a wave that's somewhere in their official band. They look for the strongest one they can find, and they monitor it. They watch it going. They have time. I mean, the electronics works fast, so it's watching the frequency, and it sees the frequency beginning to go up in frequency, and it follows that, and then it watches the frequency go down, and each time it's making these fluctuations, the radio is preparing sound for you. If you're going up in frequencies, it's beginning to make high pressure for you. If it's going down in frequencies, it's beginning to make low pressure for you. It's recreating the sound. The details of creating stereo and stuff I'll leave for another life. So, but that ability to monitor the wave going back and forth means that if there's another wave from another radio station, but it's significantly weaker, it's now in the same territory as the wave you want, but they're moving unrelated to each other. And your radio focuses on the strongest one. And it's ignoring this other one that's dithering around in the same territory. And that's true until, as you drive along in a car, for example, this wave that you've been following gets weaker and weaker with distance. And again, I'll leave that for the moment. And the other one gets stronger and stronger because you're driving toward it. Eventually, your radio begins to go, well, I've been following this one. Oh, that one's stronger now. I'll follow this one. It snaps back and forth. And that's hopefully an experience you've also had in a car driving, listening to an FM radio, that when you get into that middle ground where you've got two stations of similar strength by virtue of distance, your radio is beginning to have trouble deciding which one it's going to stick with. It snaps abruptly back and forth from one to the other. You've been listening to this program and you're all focused on it, all of a sudden it's gone and the other programs have taken over because the wave got stronger. The second wave got strong enough that it dominated your radio, snapped to follow it. Other than that, this ability to follow the wave and watch its frequency go up and down means that it's pretty immune to just noise. Like you don't hear thunders, lightning strikes on FM radio or just random electromagnetic noise. Not nearly so much. It has a slight effect for interesting reasons that I'll leave also. But FM is pretty clean. FM was created back in the day when electronics, again, was pretty simple. It was actually before the era of being able to watch the wave and really distinguish it from the other wave. Back in the day, they couldn't do that. Now they can. And they had to, it was already still kind of a tour de force to manage to do FM radio at all. And now modern electronics has made it so that this allocation of 200,000 cycles wide around the center, you can do a lot in that if you use fancy electronics. You can watch the waves moving around, and you can watch the intensities of the waves changing and stuff like that. So now modern transmissions include, some of the stations will transmit not only their main transmission, but they'll send also other information along, like some digital radio stations. They tack them into the same bandwidth and manage to get them to you. All right, it's okay? So just a lot of story, but a lot of talking. Yeah, Fiona?
This is kind of a tangent, but I have an app on my phone that lets me listen to radio from other countries. And I'm wondering how that works.
If you're listening to, so Fiona's saying that she's got an app on a radio that lets you listen to radio from other countries. And probably at some point, the radio is going into the internet, is moving by way of internet and then coming back to you. So that may not actually be that you're receiving the radio. Somebody's receiving it down there, and then recreating. So they've got an FM receiver. They're watching the wave go back and forth. They're taking the air pressure fluctuations, and now they're encoding that no longer in a radio wave, but in some other form is probably going by optical communication. So they've encoded it now, and it's still an electromagnetic wave, but it's now in a light wave. And the light waves, we'll talk about optical communication later, but light waves are used to encode information as well. You can wink them on and off, which is the easiest approach. So it's essentially AM modulation, but it's going in light. And they can travel hundreds of kilometers, and then they're periodically picked up and recreated and sent on their way again. Is that okay? Yeah. A lot of phones also have FM receivers in them too. Do you guys listen to FM radio on your cell phones? Yeah, I think it's in there. It's kind of like, no, why would you bother? I think you have to plug your earphones into it in order to provide the antenna it needs. So I haven't kept track of this, but okay. My guess is you all have FM radios in your cell phones, whether you noticed it or not. They're there. They need the antenna because the physical size of the cell phone is too small to be even a modestly effective antenna for FM. They want something long, so they use the cord of your earbuds. Last thing to say here before I leave this, and I got to leave it. Otherwise, we can major in radio. Is that these encoding schemes, AM and FM, they grew up in the era of simple electronics. Modern electronics can look at these waves essentially in real time. They can watch the charge going up and down your antenna in a way that people 70 years ago just couldn't even imagine. So they can watch the charge going up and down, and they can pay detailed attention to everything going on. And the result is that what can be encoded on the radio wave by just subtly changing how you're moving the charge up and down the transmitting antenna, and therefore the response of the receiving antenna. Very subtle things. And so that's why so much information can now be sent in the same bandwidth that used to be involved just for, say, AM audio or FM stereo audio. This is all part of like your cell phones, Wi-Fi, all those. They pack so much information into a narrow range of wavelengths. They're all now modern tour de forces. That happened to television. Television grew up in an era when the electronics was simple, and Channel 5 or Channel 10 or something like that, they could present a gritty picture, low resolution. You guys can't even imagine the low resolution anymore. You see it in movies, and you're like that's television. Using the same bandwidth now, they can send high definition television. It's just, you guys take it for granted. It was fun to watch it evolve, and the science and mathematics behind making it possible is itself kind of a fascinating story. But I'll let that one go. Okay, so that's the story of radio. Let me just show you radio actually before I totally forget it. So this is an FM receiver over here. It's listening at 88 million cycles per second, 88 megahertz. It's looking for a wave coming at it, and it wants that wave to be dithering back and forth in frequency around 88 million cycles per second. And this guy is a little transmitter that transmits at 88 megahertz. And when I talk into this, I'm taking the wave that it's sending out of this antenna, which again is too short to be a properly resonant antenna, although I think it's got coils in here to effectively lengthen it. And as I talk here, or press the gadget's play, it's taking the frequency of this wave and dithering it. And one thing I want to say, no, there's no evidence of sensitivity to orientation of the antennas. If this thing should be sending out primarily a vertically polarized electromagnetic wave. What I'm trying to do is see whether I can get a situation where it cannot receive the wave, but the answer is no. probably for boring reasons. And the boring reasons are that this wave that's going out, it's going all over the room, it's bouncing off everything. So even if the wave doesn't push charge up and down on that antenna perfectly by direct shot, it can bounce off something and come back in and have a second opportunity. And probably this thing's just being bathed in reflections. It's like I got a light bulb here and the room is filled with mirrors. You can see light all over the place. Gone. And now it's looking for a wave and it's finding bits and pieces from elsewhere. Is that okay with everybody? It's turned into objects that are themselves sort of magic, which is unfortunate. If they were a little more, a little simpler, they wouldn't seem quite like they happen all by themselves. All right. So microwave ovens is a story, it's really the same story continued. Microwave ovens are still electromagnetic wave-based systems. The difference is instead of trying to convey information with the microwave, with an microwave being an electromagnetic wave, they're used to heat food. But otherwise, lots of similarities. So half the fun of this is doing the things that you're not supposed to do. If you put a CD in a microwave oven, it will. You okay with the question? Do you even remember what CDs are anymore? These other things, like these showed up over the course of my teaching this class, and now they're kind of like, what are those? If you put a CD, how many think, A, nothing will happen when you put it in the oven? How many think it will burn up the oven itself? How many think it will burn up the CD? Yay. All right. Lest I go too far without burning up a CD. So, yeah. So CD. Instantly, a CD consists of an exquisitely thin metal layer in plastic. And the metal layer has features on it that represent information, sound information. This is one of the demonstrations. You can actually, I'll do 4 seconds. You can do it in your own microwave. It doesn't hurt the microwave. You don't want to do it for more than 4 seconds. There'll be 2 seconds of warm up, followed by 2 seconds of fun, and then you want to stop because the next time is just to stink up your room. Here we go. So 2 seconds of warm up. Ready, get set, go. And 2 seconds of fun. You okay? Do it again, do it again. So freshly cooked. Right. And part of what this is showing you is that microwave ovens there really is an electromagnetic thing going on there. It's not a myth, it's real. Here we go, 4 seconds, ready, 1, 2, warm up, and then stop. If you go longer, it just gets stinky and no fun, right? And then you do regret doing it in your microwave. So they're fresh off, fresh from the oven, a little warm, nothing big, no big deal. So why does that happen? That exquisitely thin layer of aluminum heats up. The microwaves, they are electromagnetic waves, and like any electromagnetic wave encountering a conductor, it pushes charges through the conductor. So that aluminum layer starts to have electric current flowing in it. And sort of up until this point, most of the time I've talked about currents needing to flow through circuits to go a full loop like in a flashlight, through the battery, through the light bulb, through the battery, through the light bulb, over and over. Well, hopefully you noticed that with an antenna, there was no circuit anymore. I call it a tank circuit, but it's a wire. It's really got only one direction to travel along it, or it can go up and down. And when you're working with electromagnetic waves, there really is a lot of everybody go one way, everybody go the other, back and forth. You can get currents flowing. They're not continuous currents, they're alternating currents, but you can get in situations where you have alternating current, you can make them happen without a circuit. And that was happening in the CD. Currents flowing back and forth through that aluminum layer, which is only, it's something like 10 nanometers thick. If you walk from one side of the surface of aluminum to the other, you would pass like 50 aluminum atoms. It's really thin. Actually, just in general, you can see through CDs and DVDs if you hold them up to light. They're so thin. So currents flowing through this very thin layer, it easily exceeds the capacity of the layer. Remember, wires don't carry current for free. They get hot, and the heating goes as a square of the current. The aluminum gets hot. As it gets hot, it heats up the plastic. And the plastic, aluminum and plastic, both of them get bigger as they get hot. They swell, thermal expansion. Hopefully you've seen or paid some attention to thermal expansion. And the plastic swells more than the aluminum. It does. And it tears the aluminum layer. So the first 2 seconds what's happening is the microwave oven is warming up, is beginning to be able to produce microwaves, and it is heating aluminum and causing the aluminum and plastic to swell, and the aluminum then tears. And once the aluminum tears, it has sharp edges, and charges that are being driven back and forth in it by the microwaves pile up on the sharp edges. And if we remember what happens when you put a lot of charge on a point or on a thin wire or a sharp point, you get corona discharges. Remember those? So that was the sparky stuff. Was discharges, corona or otherwise, between the aluminum sections. So as a public service announcement with microwave ovens, and they've told you, you've heard your whole life, never put metal in a microwave oven, which is way too strong. You can put metal in a microwave oven if it's thick and dull, like a spoon, like not a punch cheap cafeteria spoon, but like one that's fancy, you buy it. It's heavy metal and it's got nice rounded edges. Nothing much will happen to that. Same with a lot of aluminum metal baking containers. As long as they don't have sharp edges and as long as they're heavy metal, they're fine. Furthermore, the walls of the what I call the cooking chamber, the microwave's box, they're all metal too. So you should already be suspicious that metal in a microwave oven is a little bit overstatement. So don't put things that are sharp or thin in the microwave oven. Sharp, thin metal, bad news. The extreme case of that is a twist tie. The thin metal wire that lives inside of the paper or plastic that is a twist tie. Those guys are wonderful. They're wonderful antennas for microwaves also. They typically are nice little dipole antennas for microwaves. Current goes back and forth and then piles up on the sharp tips, shoots sparks out the end. It's a race to see which happens first, whether the sparking off the end kills things or whether the wire getting red hot and lighting things on fire kills things. All right? So that's where we're headed. I now got to give you more idea of how microwave ovens cook, and then we can put more stuff inside. They cook, microwave ovens cook food internally. What do I mean by that? Conventional cooking is from the outside of food in. So if you put a burrito, you put a burrito in the microwave oven, or you put it in a normal oven, the outside gets hot first, and the heat propagates into the center of the burrito. And so if you bite into it, typically the center is the coolest thing if you haven't cooked it adequately. With microwave heating, it's different. With microwave heating, the electromagnetic waves go into the food, and they heat it somewhat uniformly. It's not perfectly uniform. We'll get there, but it tends to cook essentially from the inside out. This is one of the reasons why a lot of foods don't cook well. Microwave ovens are better for heating than they are for cooking, so that you often get soggy surfaces because you heat the inside, steam develops there, goes out, and you get like a bagel cooked in the microwave oven or heated in the microwave oven. It often has a chewy, soggy outside, whereas a bagel heated in a conventional oven has a crisp, crunchy outside. All right, they don't defrost food well. There are a lot of observations that we can make, and there are these classic questions like, is the food dangerous in various ways once you've cooked it or heated it in a microwave oven? So just to go through these questions a little bit, how does a microwave oven cook food? And to look at that, microwaves are another part of the electromagnetic spectrum. They are still electromagnetic waves. They happen to be electromagnetic waves with high frequencies and short wavelengths. In fact, the wavelength characterizes the microwave. A microwave is officially any wave that has a wavelength shorter than 1 meter, down to 1 millimeter. So that range of wavelengths, from this to this, these are all microwaves. And so the microwaves start at 300 megahertz, and the higher frequencies, they go there. So most of what you use these days, your cell phones all work with microwaves, Wi-Fi is all microwaves, microwave ovens are microwaves. This was hard, difficult territory in the days before modern electronics. In the days of tubes, it was tough. In fact, one of the innovations of World War II was what's known as the magnetron. It was created with the idea of making radar work. So it showed up in World War II. The magnetron is also present in a microwave oven. That is the source of microwaves in there. So you're using basically World War II technology. It's very inexpensive, very simple, and it transmits microwaves, and very intense ones. It was great for radar. It's great for cooking. Yeah.
So water will respond to the electric field. Does nothing happen if you drive through the microwave?
So if water responds to the microwaves, does anything happen when you put dried fruit in? Dried fruit isn't completely dry, so it's got enough water in it that it still heats by way of the water. But there are things that are pretty essentially dry, like salad oil. Some of those, they still heat. Now it's not the water doing it. But most of the heating that takes place in a microwave oven, most foods, have enough water in them. That's the dominant thing that goes on. And I'll show you how the water absorbs the microwaves and turns the microwave energy, the energy in the electric and magnetic field of the microwave, turns it into thermal energy. It's true that everything else you put in there will get hot eventually. There are some things that are very resistant to it, like glass and some of the plastics. They're really nearly oblivious to the microwaves. But nearly any food will heat to some extent. Incidentally, ice doesn't heat well at all, even though it's water. And it turns out that the ice doesn't heat well because we'll see that the way it absorbs the energy is by rotating. And if ice, because the molecules are sort of stuck in place and can't rotate, ice doesn't absorb microwaves well. And so this leads to what I always thought of as the frozen burrito problem, but probably time has marched on and it's other frozen foods for you all, where you put the frozen food in right out of the freezer, you put it in there, you blast it for some amount of time. Okay, so for me it was a burrito, and you bite it, and it's Russian roulette. You bite into the burrito, some parts are still frozen, and other parts are like lava. Right? Is this familiar to everybody, this problem? The problem is that where it is frozen and truly frozen, yeah, it has water in there, but the water can't rotate, and so it doesn't absorb microwaves well. But any part that manages to thaw, for whatever reason, now it's got water molecules that can rotate. They can absorb microwaves, and they do, and so you get this catastrophic drift. The frozen parts stay frozen, and the ones that thaw get all the heat, and they diverge. And now it's the Russian roulette bite. I suppose it's probably pizza too, frozen pizza. Crunch, crunch, crunch. Oh, it's frozen, and you got whatever it is stuck to the roof of your mouth, or the roof of your mouth stuck to the pizza. I'm going to skip these various stories of of the transmitter, I'm just going to tell you that there is a transmitter inside this box. It transmits at 2.54 gigahertz. That is, a gigahertz is 1 billion cycles per second. So it's 2.5 billion cycles per second. It's the same territory that's used for old Wi-Fi. There's now modern, faster Wi-Fi is 5 gigahertz, but these are very high frequencies. And the wavelength at 2.5 gigahertz, the wavelength is, it's about 11 or 12 centimeters. So it's about like that. So a quarter wavelength antenna for a wave that has a wavelength like that, quarter wavelength antenna is about this long. Little teeny guy, and there is a little teeny antenna inside the box of any microwave oven. It's usually hiding behind a little plastic or plastic-like cover. If you pop that off, it's in here. I could pop it off, and I've sometimes shoved cameras in there to let you see. You go in and you're in a camera looking into a room, and what do you see? You see the little antenna sticking up, sitting at the end of a little pipe. And that antenna comes right out of the magnetron. The magnetron creates the electromagnetic waves, and it transmits them with the little antenna. Okay? Those waves go into a box that has metal walls, and metals reflect electromagnetic waves. I told you about last time. And this box, it's got 6 sides, right? A rectangular box has 6 sides. 5 of them are obviously metal. The 2 left, right, top, bottom, back. The front is also metal. The front surface of the microwave oven, you've looked at microwave ovens your whole life, and they never give you a clear view of what you're cooking. You're always looking through this screening. It looks like a plastic maybe with little holes in it. And why couldn't they just take off that stupid screening? Well, that screening is the 6th side of the box. It too is metal. It has little holes in it. Why don't the microwaves go through those holes? Well, it turns out that electromagnetic waves are basically unable to detect structure that is considerably smaller than their own wavelength. So what does that mean? If the wavelength is this long of the microwaves, and you have a metal surface that has a hole in it that's only this big, the microwave, oddly enough, won't be able to detect that hole. It won't go through the hole. It'll try, but it won't manage to get through there. Why? Because as the microwave is in the process of trying to get through the hole, currents will flow around that hole, electric currents, and manage to compensate for any processes that would carry the wave through. Nonetheless, despite the fact that there's a hole there, the currents manage to absorb the microwave perfectly and retransmit it backwards, reflect it. So it's as though the holes don't exist. So the box is completely sealed by virtue of having a mesh on it with holes much smaller than the wavelength of the wave. All right? Water heats. I'm running out of time, so water heats because water molecules are what are known as polar molecules. They have a positive end and a negative end. I think of them as Mickey Mouse's head. I don't want to get in trouble with Disney, but they have 2 hydrogen atoms up here and an oxygen atom, and the oxygen atom doesn't play fair. It steals electron density off the hydrogen atoms, leaving them with somewhat of a positive end. So Mickey's face is negatively charged slightly, and his ears are positively charged slightly. And the result is when you put water molecules in an electric field, they rotate to try to align with the field, their polarization with the field. And since this field of a microwave oven is fluctuating from pointing first one way and then the other, the water molecules flip back and forth. They're trying always to align with the field, and they bump into each other as they rotate, and they get hot. So that's the story of the heating. The story of fun and games, which I don't want to completely omit here. If you put things that can carry electric current in them, they will do so. And so, things. A light bulb. So this is an old-fashioned Edison-style incandescent light bulb. And we're driving electric charges back and forth in it. And can you see it glowing? The charges are going back and forth. There are sharp points on those structures that shoot charge out of them into the gas that's inside a light bulb and light it up. So that's an Edison style. Here is a compact fluorescent, same idea. Okay? It's clearly very electric, lots of electric stuff going on there. All right, I got to do the good one is this one. Here we are. If I put, I'm going to burn a match in here. So there goes the match. I'll put a dome over the match. And it will drive charge back and forth. Can you see? What you can't see is the glow up on top. Can you see it now? There's a ball of it's hard to see it up there. There's a ball of plasma in there. I'm going to stop this before it explodes on us. All the other demonstrations you can do in your oven. This one, do it in your friend's oven. The charges are going out into the air. The air is becoming electrically charged. And once that happens, it's not called a gas anymore, it's called a plasma. And the plasma can absorb microwaves. And it gets very hot, so we had a big ball of plasma on the top. You can come see it from ground level now. As you walk by, I'll get it back in gear and you can watch it plasma.